Okay. Let's get started. So, I want to just kind of briefly recap. We did like a whirlwind intro tour to relational databases and relational models. So remember, we had this library example where we started by trying to put all this information into one table, like patrons, phone numbers, what books they have checked out. And there were problems with that, and we separated them into separate tables or separate relations in order to solve a lot of those problems. Now we have relations that are very well defined, that are easy to reason about, and that are easy for a database system to reason about. And then it does make it a little more indirect, the way that we have to go about answering questions. Instead of just finding one row for Joe and find all of the books that Joe has checked out, we kind of have to start where the Joe name lives, use some indirection to get some other table, and there are a few steps involved. So we saw basically, that's not really a problem. We saw basically how all of this happens. And it's not a problem because these tables have data structures built around the interesting columns. So if we need to quickly find Joe, we can do that. That gives us another key. We can take that key to quickly find whatever else in some other table. And because the data is structured, is what allows us to do this. I know that every record in one of these tables or relations will have a name, a major, a so-and-so, and whatever. And I know what the type is of those fields. I know that name is a string. I know that GPA is a number. So I can build a tree or a hash index on any of those columns that I want. Okay. Now I want to reiterate. Let's look at these trees and the data. The raw data itself are just somewhere on disk or in memory. The orange boxes is the raw data. They are not necessarily in any particular order. They would be in reality, but if they're in, or say they're ordered by name, that's great. It doesn't help us order them by GPA. So that's not a problem though, because we can build auxiliary data structures that by just adding one level of indirection, we can now point to them in some arbitrary different order without actually rearranging the orange records. If I said, all right, I want to find people by name, so let's sort the entire database by name, and we're talking terabytes of data. And then I want to find them by GPA, so resort it all by GPA. That would never work. These trees here, all they have, they don't hold the raw data. They hold some small piece of the raw data, a key. One of the trees the nodes just hold a name plus a pointer to the full record. The other tree, the nodes hold a number plus a pointer to the full record. Okay? And so that's kind of what today is all about, is these pieces of information that are used to build these data structures, a subset of the full information, and it's called a key. But we need to kind of reiterate the formal definitions of what we're talking about, because I'm going to say them a lot, you're going to see them a lot, so it's important to get it down. So a schema is basically the description of the data, not the data itself. It's metadata. So it's basically name and type. There will be a little more that goes into a schema. But this is the fundamental requirement of a schema, is every column has a name and a type. And then, so each one of those things is an attribute. That's the name-type combination. Here's an actual schema. There's no instance data associated with a schema, but it gives us enough information to reason about it. And we don't really care what the data is. we have like a higher level picture of what it means. And then the data itself is an instance. Okay? So an instance is comprised of tuples, one or more tuples, where the tuple is just the full row. It's some combination of individual data cells. And this, all of this together gives us a relation. Okay, and then remember, it's very important to keep in mind, oh, by the way, check out Hermione's GPA. It's very important to keep in mind that a relation is kind of just, it's one set of schema plus instance data. We can have another compatible relation that just has a different set of tuples in it. And this will happen all the time. I might start with the table on the left, do some operation to it that results in the temporary table on the right. Or it might even be relation 1 turns into relation 2 after deleting a couple of rows. So this could be like a permanent change to relation 1, or relation 2 could be a temporary thing that I use to answer some other question. So I'm saying, first give me just Harry and Hermione, and that gives me a temporary relation. Then I could take that and do something else. Is there a question back there? Attribute is just it's basically the column header. It's the column name plus its type. So a schema is comprised of multiple attributes. Well, not necessarily multiple. You can have a single column relation in a database. Okay, and then finally, a relation is the instance data in a relation is a set of tuples. So it's meaningless to have duplicates for the entire tuple. You can obviously have duplicates for some of the columns, but not the entire thing. And that basically brings us to where we left off on Monday. So, and this is the idea of keys. A key, every relation has to have at least one key, and a key is what uniquely defines the tuples, or uniquely identifies the tuples. In the students table, I had to actually add a column in order to make a key. That's the only reason the SID column exists, is to uniquify all of these tuples. Without SID, it's very unlikely, but still possible, that two students will have exactly the same name and exactly the same GPA. Right? Unlikely, but we can't just rely on the unlikeliness of it to solve the problem. And then over in like the vehicle models table, I kind of changed this from what we saw on Monday to make it more clear. Any manufacturer can obviously have multiple models, so the manufacturer can show up multiple times. And then the same model could show up multiple times, like maybe Toyota and Subaru both make an F1 car. So we have to take the combination of the two in order to uniquely identify a tuple. Okay. And then we left off here. Started with, before we talk about keys, we're going to talk about super keys, which is kind of less strict. So super key is a set of fields such that none of the tuples in the instance are duplicate. Okay, so that's, that's basically, that's pretty straightforward. This is just defining uniqueness. Question? So fields, yeah, replace that with attribute. Basically, it's a set of columns in the table or in the tuples. Okay, so I'm just going to draw some stuff here to talk about super keys. I'm going to draw a relation where we don't really know what the data means. We're just going to look at the values, and it doesn't matter what the data means. So I'm just going to give the attributes kind of meaningless names, A1, A2, and A3. And then I'm going to fill this in with some instance data. So let's say there's like X, Y, X in the A column. 4, 4, 3. So these are different types. You know, one of them is maybe like a character or something. One of them is a number. Doesn't matter though. Like I said, we don't know what this information means. We're kind of just abstracting away and reasoning about the uniqueness of the data. And then we'll have like Q, P, and X. Okay. So superkey is a set of attributes or a set of fields such that there are no duplicates among the instance data. So set of attributes. So a set means just a group or combination of things that is unique. So what are all of the sets? Taking these three attributes, A1, A2, and A3, what are all the possible sets I can make, all the combinations I can make out of those three things? Well, we can do A1 by itself. That is a set. We can do A2 by itself, A3, the combination A1, A2 is one possible set here. So basically I'm just enumerating all possible combinations here. A1, A3, A2, A3, and then all of them. Okay. These are the sets of attributes. Now we want to know which of them are superkeys. And so what does superkey mean again?
Two fields that have unique values. A set of fields.
A set of fields that have unique values. So let's look at the sets. A1. Are the values in A1 unique? Nope. A2. Nope, we have duplicate 4s there. Okay. A3? Yes. A1, A2. So we're looking at now the tuples here of the two columns combined. So yes, even though each of those columns has duplicates within itself, the tuples, there are no duplicate tuples. We have x4, y4, and x3. So yes, it is a superkey. A1, A3. So this one, and in fact the rest of them are actually very easy to answer. Question back there.
I'm just a little confused on what the difference is between just key and superkey.
Okay, so just key versus superkey. Yes, we will get to key right after this in a second. Yep. But the rest of these all are easy to answer. And the hint is because they include A3, so A3 by itself is unique. Thus, any tuple containing A3 is also unique. Because you cannot have a duplicate if you're never going to get a repeated value in A3. So we can just say yes, to all of them that have A3. Okay, makes sense? There's no way you could create a duplicate no matter what you put in A1 or A2. If you can't repeat A3, you can't get a duplicate tuple.
So it wouldn't be a duplicate if you had two tuples with the value swap. So x3 and 3x would not be.
So I'll just kind of draw over here. So if I had like x and 3, well, I'll use both letters. Let's say like x and c versus c and x.
Yeah.
Those are not considered duplicate. Because the attribute is very important here. Like, you know, this attribute versus that attribute mean different things, so swapping them means a different thing. Yeah, good question. Okay. Yeah, back there.
Maybe, I guess the difference between the key and the super key, doesn't a key have to be, like, even its combinations have to be unique?
A key, yes, a key also has this uniqueness requirement, yes. And so a super key is, that's it, is basically everything in the tuple has to be unique. And we will get to the difference between a key and a super key in just a second. We have to kind of just start with the basic definition first. Okay. Now I'm going to do something else. Instead of starting with some instance, which we don't even know what the meaning of the instance is, we're just saying, all right, assuming that that is the final data and nothing will ever be added, then we know that like A3 is unique. So we can kind of say that reason about uniqueness here. But it usually goes the other way around. We have to define some problem and thus define, instead of taking the data and saying, well, here are the rules about the data, we define the rules first, which is what specifies what data is valid. So I'm going to do more like a real world, give like an English description of a problem first, and then without even seeing any data, we will reason about what fields need to be unique. So we'll do just the students and enrolled, kind of like what we've been seeing. So here's the enrolled table. It has student ID, course ID, and grade. And then the students table has student ID, name, and GPA. And then I'm not going to fill in any instance data. This is just the schema, and we want to just kind of reason about as people, as humans, we want to reason about what this information should mean. So let's go over to students first. Let's say, like, what are the super keys for the students table? As I've already said, SID, the only reason it is there is to uniquify. So SID, oops. What are you doing, PowerPoint? SID is a super key because by definition it's always unique, which also means that SID plus anything is a super key. Okay? So we'll get the easy stuff out of the way first. Now what about any fields not containing SID? So is name a super key? No. Obviously you can have two students with the same name. Is GPA a super key? No. Is name plus GPA a super key? No. even though probably in reality there are no two students with the same name and exact GPA, but we can't prove it. So those are the super keys for students. What about the enrolled table? Is SID a super key? So to help answer this, let's start filling in some instance data. Let's say student 1 is enrolled in course X with a grade of A. Now, in order for SID in this table to be a super key, the SID 1 can never show up again, which means student 1 cannot also enroll in course Y. So SID by itself is not a super key. By similar reasoning, CID, like if I wanted student 1 in course X, if CID was a super key, then I could not have student 2 in course X. So SID is not a super key, CID is not a super key. Every table has to have some set of fields that are unique though, so there is a super key here. What should it be? We are the ones deciding what it is. Yeah?
Combination of SID and CID.
So combination of SID and CID. Yeah. This means I can have the same student show up twice as long as it is in different courses. And I can have the same course show up twice as long as it is a different student. All of these tuples here are unique because the two of them combined are unique. Okay? So if SID CID is a super key, that also means that SID CID grade is a super key. Here's kind of where the critical difference between super key and key starts to come in. Technically, this whole thing is a super key, but we don't want to actually include grade in the uniqueness constraint for this table. Okay? All right. Now, a key, just a plain old key. The definition is built on the definition of a super key. So first, it's just the uniqueness property of a super key. So a set of fields is a key if it is a super key, and no proper subset of its fields is a super key. So what does that mean, subset? If I have some set A, B, C, a subset of that is anything that contains elements from just that set and is also a set. The proper part means that it doesn't also include the full set. So a subset is any of these elements may be taking some of them out, but a set also technically includes the full thing itself. So proper subsets here would be A by itself, B by itself, C by itself, A and B, A and C, B and C. Not A, B, C. Okay? So, still pretty straightforward. We have to have, the combination itself has to be a super key, meaning just unique, and then we have to go look at all of its proper subsets. If any of them are also unique by themselves, then we don't have a key. We just have a super key. Okay, so what does this mean? In what there's a critical difference between the two. So here's the answer we basically just came up with. We had that instance data. We filled in the yes or no, is it a super key column for all possible combinations of A1, A2, A3. Okay. Now, is A1 a key? Well, it's easy to answer. It doesn't even pass the first test. It's not a super key. So anything that's not a super key is also not a key. Now, the rest of these might be keys because they are super keys. So A3. Are any of its proper subsets super keys? Doesn't have any proper subsets. So yes, A3 is a key. A1, A2. So it is a super key. Its proper subsets are A1 by itself and A2 by itself. Are either of those super keys? No. We can either just look in the existing table, no, they are not super keys. Or we can just answer that question again, no, A1 has duplicates, A2 has duplicates. So yes. Okay. A1, A3. No, because A3 is a super key. And similarly, we can just answer the rest because all of them have A3 as a proper subset, which by itself is a super key. Okay. So, yeah, so that's kind of just what we wrote. Answer column filled in. So usually, database design, so usually it goes kind of the other way around. What we did here was we had some meaningless instance data and we were just asking, assuming that this is the final data and no other data is ever going to be added, we now know what is unique and what is not, so we can kind of just reason about uniqueness. That's not the way it works. We as database designers think about the problem first and then define the keys. The data doesn't define the keys, we define the keys, which restricts what is valid data. And this is basically, this is the tool we use. This is how we define what the database means. I could, so I could go back to this example where I have the enrolled versus the students table. I'm the one who decides what the keys are. I could pick anything here. I could pick GPA as a key on the students table. And that would mean I have a university where no two students can have the same GPA. The first one to get a 4.0 ruins it for everyone else. But that's why we don't pick that as a key, because we define what the information means. So a database designer's job is to take the description or knowledge of the problem and produce schema. The schema is the definition of the meaning behind the data. Okay? So this is kind of analogous to you as a programmer. You take some description of a problem and you design code or an algorithm that solves it. Okay, so I want to do another little exercise with the same enrolled table. So what is the key? We don't define super keys on tables in real relational databases. We define keys. We have to know kind of what the super keys are first before we can do that. So we have no instance data again. And we are going to define what is the key based on us being humans and having an intuitive understanding of what we want the information to mean. So we already kind of decided that what we want is SID, CID to be unique. So let's go with this. Let's say this is the key. What this means is basically a student cannot take the same class twice, or a student cannot show up in this table having taken the same class again. But we're the ones deciding this, so let's pick a different key. What if our key was SID? What does this now mean?
This means that each student can only take one class.
Yeah.
And on that first note, it might be wise to make the key SID, CID, and then semester, so that the student can take the same class again the next semester.
Yeah. So the answer, yeah. So maybe we do want students to be able to take the same class twice. We'll get to that. This answer here, if just SID is the key, what this database now means is a student can take one class at the university. What if it was just CID? So a class has a maximum enrollment of 1. Yeah.
Is there any way to let someone know that hey, this is the key that we use? Like if another program looked at that database, would they just have to guess?
So right. So is there a way to let somebody else know what the keys are? Yes, the keys are available to the user of the SQL database. You can see what the keys are. But an even better way is to look at the documentation for the tables, which is not in XML, or sorry, not in SQL format at all. It's like a more abstracted way. It has nothing to do with a particular query language, but it's more like a diagram describing the data and the relationships between different pieces of data. And we'll get to exactly how to document a database next week. Okay, let's look at another one. What if I did actually, you know what? This is an exercise I have coming up for you, so I won't do it. But so you hopefully kind of get the point. We could pick any key we want here, and the key we pick is what defines what the data means. If for some reason I wanted a maximum enrollment of 1, then I would pick CID as the key. And it's a little counterintuitive, but adding more to the key kind of makes it less restrictive. So by adding SID to the CID key, I've now allowed more people in the class, and I've now allowed students to take more than one class.
If the super key is SID and CID, and if the student repeats the class, does that wipe out the first set of questions?
Right, so if the top one here is the key, and if the student repeated the class, that means you would have to wipe out the existing one and replace it. So SID and CID would not change. So what this implies is the grade would change. And that is the actual meaning that we want. If you take a class twice, it doesn't show up on your transcript twice. It replaces your old grade. Yeah. Okay. Right, so there's the answer. The key is SID plus CID combined. And this allows for one student to take multiple classes, multiple students to take the same class. Hermione has A pluses in all of her classes. That's the most important to get right. Okay, so the database DBA means a database administrator, or the database designer, which will be you for this class. You specify one special key called the primary key. You can specify multiple keys or just one key. Every table has to have at least a primary key. And if you have, there is a situation where you might want two different keys. So far we have not seen that. We've seen a complex key, but this is still just one key, SID plus CID. There are situations where you would want this key plus another key to define the data differently. And those additional keys, well, all keys are called candidate keys, and then one of them becomes the primary key. Again, this is all not in the context of any particular query language. This is just abstract database design. SQL will let you create a table without specifying a primary key. And it's not like just violating relational database design in such a severe way. What it actually does is kind of behind the scenes, it just adds a hidden column to your table and makes that the primary key. So don't let the SQL engine decide what your primary key is. You should always specify one. So candidate keys. I'm kind of getting into like very pseudo SQL syntax here. We can specify additional keys. So I'm saying there's a primary key, and then I'm using UQ for an additional uniqueness constraint, which is, so I'm saying SID CID is one of the keys. SID grade is another key. As far as what these two things mean, they're the same. They both just mean those two tuples have to be unique. The difference between primary key and candidate keys we'll get to in a second. But given these two uniqueness constraints on this table, what would this mean in English? Like, what's an English description of this?
You could only have one grade. You have the unique grades. One student can have the same grade in two classes.
No one student can have the same grade in two classes. Let's get another option.
Would it be adding the grade to be part of the set of unique keys?
Yeah, so it is it's adding grade to one of the sets of unique keys, but it's not involved with SID CID. It's the relationships between these things is important, and the combinations that you put them in has very different meanings. Is there another?
Does it just mean that every student can be in only one class, and every class can have only one student? And the second one means every student has to have a unique grade, like they can't have the same grade.
So the first one is the same thing that we had before, SID CID. So the first part means a student cannot take the same class twice. The second one, let's look at that. So let's say I had student ID of 1 with a grade of A. This allows also for student ID of 1 with a grade of B. So it's kind of tricky to get to the real meaning here. I could not have any other combination of student ID receiving an A, even if, so let's say this is class X, this is class Y. I cannot have these two things repeated. So what this means is, like, if you get an A, it's like you've used up your A. You can't get any more. You can take another class and you can get an A minus or a B or something, but you'll never get another A. Yeah. So it's kind of subtle. You have to think about. It usually helps to just draw things out like that to arrive at the meaning behind what these keys mean. But we define the keys, and that defines the meaning of the data. Okay. So I have an exercise. I have 3 different problems that I want to solve with a database. You may think these problems are really weird, but maybe someone has this problem and they want to solve it. So I've just put up the schema here, CID, SID grade, and I want keys combined with this schema that will solve these 3 problems. So to specify these keys, just do it kind of like this. PK and UQ. Don't worry about the difference between PK and UQ. They mean the same thing for our purposes. You can only have one primary key. So with the people around you, discuss and figure this out. Okay. So let's see what we came up with. So I actually kind of just thought about it a minute. This second one is a little poorly specified. We kind of already said that a student, with our existing solution, a student could retake a course for a different grade. But they can retake a course for a different grade and keep both on record, is what that one meant. So this first one, though, a student cannot take the same course twice, and no two students can receive the same grade in the same course. Anyone want to offer a solution? Yeah.
SID and CID would be one.
Okay, so we'll just do primary key, SID, CID. Oops, not QU. UQ. CID and grade? Yes. So, restricting course ID plus grade to be unique. So this is a little counterintuitive. This problem states no two students can receive the same grade in the same course. But students is not actually involved in that constraint. So what this means is, let's say I had course X with an A in it. This could be student 1. I could have student 2 in course X, but this cannot be an A. So since student 1 got the A first, student 2 cannot. Some really old school professors actually kind of curved that way. They're like, there will be 10 A's, there will be 10 B's. Like, even if you get 99%, you could get a B in theory. So, it's not that unreasonable that you might define a database kind of like this. Okay, a student can retake a course for a different grade, and both will show up in the records. Who wants to offer their solution?
We thought that if we did a primary key of SID, CID, and grade.
Yep. So SID, CID, and grade all in the same key. This basically just means, so I could have student 1 in course X with an A. I could also now, the student can be in the same course with a new grade. This is why, this is the critical difference between a key and a super key. Remember that when we defined the key to be just this, the addition of grade is also a super key. But if I include grade in the key, it has a very different meaning on what the table defines. Was there a question back there? Could you have, yes, the same grade could show up twice if it was in a different course. Or sorry, if it was a different student, yeah. So same course, same grade, different student. Yep. As long as all three of them are included in the key, so that just means the combination of all three has to be unique. Yeah.
So this is assuming that if you retake the course, you won't be getting the same grade the second.
Right. So this means if you retake the course, you will not get the same grade, because otherwise you would just have 2 records on there that are duplicate. So if you wanted to allow for that, you would have to add an additional column, like was suggested, maybe like which semester was the course taken. Okay, and then finally, a student can only take one course and receive a single grade for that course, and a course has a maximum enrollment of 1. Jack. Come on. Primary key SID. Unique candidate key of CID. Yep. So the first, like before the comma, the first part of the sentence, a student can only take one course. That is handled by the primary key. And then course can only have max enrollment of 1 is handled by the unique. Could you swap the two? For these purposes, yes. They mean the same thing.
Like it's not well defined by the database system.
The database, they do have a different meaning. They do have a special different meaning. But as far as we've talked about so far, all they mean is uniqueness.
Right.
Both of them mean that. So the point I want to make here is SID by itself plus CID by itself as 2 separate keys is very different from SID and CID combined as 1 key. Those mean very different things. And so this is just kind of what you have to train your mind to think about in terms of how do these uniqueness constraints define what is valid data? And how do I translate an English description of a problem into this in order to solve it with the database? Okay, let's take a short break, 3 or 4 minutes. So, back to this question of what's the difference between a primary key and a candidate key? For now and for quite a while even, we will not really have the details of the answer to that. We will get to it. For now, they kind of mean the same thing, but I will tell you how to pick. So here are two options that mean the same thing. I've got primary key of SID, CID versus unique key of SID, CID. So these two things are kind of just swapped. They both define this constraint, this English description of the constraint. So what you should do for now is the primary key should be as small as possible in terms of number of bytes, and they should be integer types if possible. They don't have to be, but this is kind of an optimization. The reason for this is that the primary key is copied in a lot of places, and it's used as an identifier for an entire record in lots of different places. So being small is important to reduce duplication, and being int versus like a big string or something is important for fast comparisons. Yeah. Are candidate keys actually used? Are they actually keys? Yes. How is this possible? So SID is a proper subset of both of these, but SID by itself is not a super key. Because SID can show up multiple times.
So in some constraints, this would be wrong, right?
In some constraints, what?
In some of the examples you gave, this could be wrong. It's really what you're trying to achieve.
Yeah, so this defines the data, not the other way around. Yeah. This is not wrong or right. This is the definition of the data. Yeah. Okay, so keys are not just for us defining information about one relation. They are used to relate to different tables. They're used to kind of indirectly reference another relation.
So right now, the algorithm for choosing a primary key or keys in general is just looking at the data.
Right. So for right now, the algorithm, our algorithm for choosing a primary key and keys is taking an English description of the problem and thinking about it, and then translating that into sets of keys. Yep. And then which one should be the primary key is try to make it small, try to make it integer types, or just a single integer type is ideal.
So there's like an art to this.
Yeah, more of a science than an art, but yeah, this is computer science. We will get to this. We will get more into this algorithm. We're kind of missing one key tool for how we design databases, and that is the documentation that I talked about. For first we produce documentation that describes the relationships between data, then we would actually go and make the schema. So anyway, so this here, the fact that SID shows up in both of these tables is not a coincidence. It's because they are intended to mean the same thing. So SID is a key in students table. It's not a key in the enrolled table, but it relates to another key. Now, I'm going to do like a complete 180 here. It's going to seem weird, but this will relate to this issue of keys referencing keys. So here's a little snippet of C++ code. I have some object which is created using a pointer, some object pointer which is created using new on the heap. I make another thing which references the same one. So how many objects do I have? One object. One object, 2 pointers. I delete the object using T1, and then I ask for T2.value. So assume value is some field of the object. Okay, so what happens? Is T2.value printed? Does it crash? What? Undefined. So D is the answer here. There is no way to know what happens. It'll probably actually print T2.value, but you can't prove it. That's really bad. D is the worst possibility here. This is the worst thing that could happen, because then we have an error without knowing it. What we want to happen is for it to tell us that we've done something stupid. Okay, so why did I suddenly show you a little snippet of C++ code? Here's the analogy in a database. SID in the enrolled table is essentially a pointer. So think of it as a pointer. This tuple 3 ron 4.0, that is the object that SID is pointing to. Okay, so here's the analogy. I have an object in the students table. I have a pointer to that object in the enrolled table. So what happens if I delete Ron from the students table? Like he graduates or drops out or something. This is an important problem that we need to address. What would happen here is if we did nothing, then this 3 becomes meaningless. It's a pointer to nowhere. It's even worse than like a null pointer. It still has a value, so you might think, okay, I'll take that 3 and go look for a student with SID 3, and it's not there. It's meaningless. So the problem here is what we want is called referential integrity. And that's an invariant that any references between values are meaningful at all times. So an invariant means if it is true at the beginning and there are no operations that can ever make it untrue, then it's easy to prove that it is always true, that it's invariant. And this is what we want in a good database design. We want referential integrity. So C++ lets us violate this. Java enforces referential integrity by taking away control. So Java does not have delete. Delete is essentially what let us break referential integrity. SQL might have an option, so we'll look at it. Here's one option. Still not actually SQL. We're talking about just the kind of databases in general. So one option is anytime some database query would delete something from the students table, we as the writers of software that run these queries, we would have to produce another query that goes in and deletes it from the enrolled table. Problem is the invariant is very briefly broken. Right after I delete from students and before I delete from enrolled, the invariant is broken. So, what if the data center loses power right at the most inopportune time, and then we end up with without referential integrity? The other problem is we would have to go and find all of the tables that are referencing the student table. Option 2 is let the language or the system do it, kind of like Java's approach, and SQL does provide some support. So we can tell SQL whether we want to allow this or what we want to happen when this happens. So I'm going to introduce the idea of a foreign key, and SQL directly supports us. It lets us specify that these references are actually references. So foreign key is an attribute whose values are a key in another table. So in this example, SID is a key in students and it is a foreign key in enrolled. So the foreign key by itself is not unique. So the term key is kind of misleading there. the foreign key does not specify a uniqueness constraint, it specifies a referential integrity constraint. What this means is, if a number shows up here in the enrolled SID column, it has to show up in the student's SID column. That's what I'm specifying by saying it's a foreign key. So I'm going to give you a little snippet of sort of pseudo SQL. We still aren't really going to get into it for until like next week or so, but this is, basically what we've been doing today is defining schema, defining constraints on those schema, uniqueness constraints, and now we're defining foreign key constraints. So creating the enrolled table would look kind of like this. I'd specify the attributes. So SID is an int. CID is 20 characters. Grade is 2 characters, because it could be A minus or something like that. And then I specify the primary key and the foreign key. So you specifically say foreign key SID, and then you have to say what it references. It references the student's SID. This is basically setting up a pointer. SID points to somewhere else. Okay? Questions? All right. Now the question is, so there's still this problem. Like I could have it set up, I could have the data set up like this, where something in the enrolled table references something in the student's table, and then I want to delete that student. So then the question is, what do we do when that happens? And SQL gives a few options. And I'm going to switch between kind of library and students based on which will illustrate the example better. Option 1 is delete the referencing records. So if I delete Dan from the library, SQL will automatically delete the phone numbers for Dan, because I specified that it is a foreign key. So when we would want to use this option is like if the referencing information does not really have a meaning on its own. So if Dan is no longer a patron of the library and we don't even have his name anymore, what does it mean to have some phone number that we can't tie to a specific person? So we just say it's okay to automatically go and delete that as well. Option 2 is to nullify the referencing key. So you can put null values in SQL. So if Ron, leaves the university, then we just say, all right, there's still a record of someone being enrolled in that class with an A minus, but we don't know who it is. And so we would do that if we wanted to kind of anonymize or unlink the data. If we wanted to keep the data around so we can still go and do historical analysis of GPA, for example, not knowing who the students were, but just all of the grades earned, then we might want to do that. We don't want to delete it because the other information is still somewhat useful by itself. Yeah?
What happens if you did that for multiple records of different students that were enrolled in the same course? Would you run into a problem where your uniqueness constraint is no longer satisfied because of null values?
Okay, excellent question. What happens to the enrolled table now in relation to its primary key? So this is why doing this is bad design. SID, CID is probably the primary key here in the enrolled table. So if part of it becomes null, depending on the database you're using, this is either just really bad design or it won't even allow it. By making SID part of the primary key, it's not even going to allow this to be null. So this won't work. So foreign key fixes the power outage problem. Say that again. Right. So this kind of fixes the problem of If I perform an operation on the database that breaks referential integrity, and I'm expecting another operation to fix it, you can always be interrupted in between the two operations. By making a foreign key constraint, this is all done in one operation that cannot be interrupted.
Could you not also simply delete the referencing data first and then delete the reference data?
Could you not delete the referencing data first, then delete the referenced data? Yes, that is, but then you could still kind of end up getting interrupted in between and only delete the referenced data and not the referencing data and not the referenced data. But why do it yourself when you can have SQL do it all for you automatically? Plus, this also just defines, this gives a stricter definition to the data, which is always better. So how do we solve this problem? What if we do want to do this, like if the student is no longer a student in the university, so their SID has no meaning in enrolled, but we can't do this because SID was part of the primary key, the solution would be take SID out of the primary key in the enrolled table, which basically means we need to add another column. Add a unique identifier for every enrollment whose only purpose is to uniquely identify enrollments. Then that can remain there. We can nullify the SID, and it's fine. Okay, the third option is to disallow the deletion. And where we would want to do that goes back to the library example. So let's say I'm trying to delete Joe as a patron of the library, but he has some books checked out. It's like, well, don't allow that. You have to go find those books first. Then you can remove Joe as a patron. If you just did this, then you would have no way of ever going and retrieving those books because you wouldn't know who has them checked out. So SQL lets us specify these three options. When we create a foreign key, I can say I want it to delete the corresponding record, or I want it to nullify the corresponding key, foreign key, or I want it to not even let you delete it. So if you try to delete Joe, SQL would throw an error.
We're not talking about like chasing the references around and like deleting them everywhere. What do you mean when you talk about interruptible versus uninterruptible operations? Because they both seem like they're doing the same things, but one is.
Yeah. So when I talk about interruptible versus uninterruptible operations, so have you heard the term atomic operation? So this is an atomic operation is an uninterruptible operation where maybe you have to do like A, B, and C. If it's interruptible, you could do A and then the power could go out. If it's uninterruptible, you can prove that it will either do A, B, and C, or it will not do anything at all. And the database engine has support for doing this. If it starts an operation that it needs to be uninterruptible, it will, when it comes back, it will unroll the partial operation that it did, and it will leave the database in a consistent state. It'll always work as though the operation fully completes or does not do anything at all.
We talked about how we just don't want to delete the record completely from the database, so what would be that idea? Circumstances. Would there be a difference if we were to just add another column, like to soft delete the tuple instead? Would that be different from just deleting the database?
So like this example where we're preventing deletion altogether, or it.
Like I looked at a place where they added a column called deleted, and they would never delete any.
Right. So if you want this to always be on record, like so, this is a very simple example where once a patron returns a book, it would be removed out of the checked out table, and we would have no record of them ever having borrowed that book. So this, yeah, you would need an additional column here if you wanted to keep all of those records forever. You would, even if the patron Joe goes away, you would say, okay, we can nullify like, part of it, or we can say this is no longer a proper reference to a real patron, but we could still keep the record of this book was checked out at this time. Yeah. We'd have to have additional columns to specify that.
And just to clarify, can this be defined on a table-by-table basis, or does that be defined for the entire system?
So yeah, this is all defined on a table-by-table basis. In fact, this is defined on a foreign key basis. So I can specify for this foreign key, I want to disallow deletion. For this foreign key, I want to nullify, or, yeah. Okay. So, finally, not relating to deleting or modifying the referenced information, but what if I try to add a reference to, like, some unknown person? Like, student number 5 is enrolled in some class. SQL just does not allow to do this. So it's kind of on two ends. It's on inserting information into the enrolled table, and it prevents certain things from happening when changing information in the students table. All because I specified that SID in enrolled is a foreign key that references SID in students. Okay? Okay, so this is all still mostly non-specific to any database engine or any database query language. We have to build up the tools and ability to properly design a database before just jumping in and like writing code, for example, without having thought about the problem at all. And there are other tools. So you've all heard of UML, right? There is a visual diagram system and strategy for representing databases, except unlike UML, it's useful. So we'll talk about that next week.